All right, ladies and gentlemen, we are back looking at a quick hit to a little more detailed journey into the periodic table and to some things we might be seeing in the future. Challenge of doing a quick hit on this laughably with me, but here we go, we're going to try. So as we start looking into how the periodic table is very, very generally organized, there's some very important things that we are purposely leaving out right now that we are not far from diving into that are very important, but we don't want to go a little overboard here. So we're just going to do some general description of terms and important visual cues that you'll get from the periodic table and how some things are arranged. So in these objectives, we're going to look at these things called alkali metals, alkali earth metals, transition metals. So these are all kind of new things. Halogens. We've already talked about semiconductors and metalloids. Noble gases. Sorry, don't know where that came from. That is not how we do noble. And then this is what we're leaving out. Relate the properties to electron arrangement of its atoms. One of the most important things we use the periodic table for is to be able to predict how things will react to each other. And we do that by electrons and knowing where electrons are in a given atom of an element and being able to use that information to predict how two elements will interact. Will they bond with each other? How will they bond with each other? What are different types of bonds they can make? Can they only make one? There is so much we can know from electrons, and the periodic table is our key to that. And just cliffhanger, we're going to get into that. So we want you to know names of just a few basic families. So we talked about rows. We have 7 rows here. And we call our rows periods. So this particular presentation is obsessed with groups, the columns. But periods, where the table gets its name, are the rows. So if I talk about period 1, period 2, obviously going down the line, we have, this row is clearly not that populated. Neither is this. But all these things have meaning. So why there's a gap here? There's a reason there's a gap there. And we're going to learn that reason. This thing that we see as the periodic table as an outline, there's a reason why it has characteristics and shapes that it does. But what we're going to do is the periods show trends. And we're going to learn trends that happen as you move up and down the periodic table and as you move left and right across the periodic table. But what row an element's on, or what period, is going to establish a relationship between every other element on that row. So they're all going to have something in common because they're on the same period. It's much more general, very important, honestly very important, but a lot more general. So what we're going to focus on more now is the family that the element's in. So our columns or groups we call families. So this is our group 1, and this is our group 2, then we go down to 3s. So we go across to group 18. And you will find that throughout the year, I very obnoxiously interchangeably use group numbers and family names. So group 17, as we'll learn shortly, are called halogens. This whole group. I will throw out group 17 on the regular talking about anything in the halogens. Group 17, group 17. Sometimes I'll say halogens, so it's very annoying. So I just warn you up front. But I usually always say group 1 metals. But all of these, because of the way the periods overlap, and I always say it's kind of like a typewriter. Once you get to this point, because of characteristics, ping, you have to start over back here and move your way across. Because of that, you have a situation where everything that's in the same column or group or family shares very important characteristics, and that is how they react. So alkali metals, this is the family name that we give to group 1. So everything in this column with sodium and potassium and francium and cesium, hydrogen is in the group, but it is clearly not a metal. So riddle, why does hydrogen have to stay, number 1, on top of the rest of the alkali metals? So properties, real quick, let me see if I can make this work here. Properties with alkali metals, all I'm going to say here, group 1s are the most reactive metals on the planet. They are the most willing to be able to jump into bonds with other nonmetals. They're very, very highly reactive. Put sodium in water, it will explode viciously. Anything further down the line on the periodic table from sodium, they will explode more viciously, to the point that when you get down the bottom to, I believe it's francium, it is so volatile in its exposure, because we're talking even sodium will explode when it's exposed to the air with the water vapor and air. But it's so volatile, you can't even keep it around long enough before it's reacted out. And so it's very hard to study something that doesn't stay around. Like when we make the new elements, they're just not around long enough. This one is so reactive, it's not around long enough, not unstable. But very, very, all of these are very intensely reactive. So as we move across the table, our group 2 we call alkali earth metals. Sweet, fun name. So in our family tree, we have alkali metals, group 1, group 2, alkali earth metals. So basically, very reactive, but they are less reactive than group 1. Now, this is a very, and if you can read that, good luck. But hopefully you get the point. Less reactive. And even I'll even sarcastically write it over, and it'll be worse. But that's the point here. The trick here is that there's very important things we'd say about alkali earth metals, except it involves electrons, and we're not going there yet. So what makes them special in terms of distinguishing this location versus this location has to do with electron storage and where electrons are and predictability. So since we're not doing that quite yet, we'll just say very reactive metal, but not as reactive as ones. As I tell my students in class, what you'll find us pulling from when you see a lot of problems that either we write or other teachers have written, we will pull from these groups 1 and 2 and over here on the fringes, on the ends. That is because they are very, very, very predictable in what they're going to do. I can count on group 1 metals reacting a certain way. I can count on group 2s reacting a certain way. I can count on 17s over here reacting a certain way. So as we move through, we're going to see that's going to get lost in a lot of the periodic table. I can't be able to make safe bets on how things are going to react. It just depends on what I'm using. But I can count on alkali metals and alkaline earth metals, group 1 and 2. Both very reactive. We will learn the difference and why this one is less reactive than group 1. Group 2, less reactive than group 1. Why is that? We will learn that. So we have alkali metals, group 1, alkali earth, group 2. Now, transition metals, as we move through the periodic table and we're going over towards our nonmetals, we call that the transition block. So all of our transition metals, I call it just there's a lot of derogatory terms for how unpredictable and nasty they are. Um, just from an ease point of view and ease of teaching, they're very frustrating. Except bottom line is transition metals get the right to be unpredictable because of a lot of different factors. I can't peg down how any, in general, how, we have copper, nickel, gold, silver, all these different things that you've heard of before that are in transition metals, but in order to know what a transition metal is going to do, and if I wanted to use it in an equation, we would have to tell you specifically about that particular atom. It's not just about copper. So in this case, if I have copper, which is Cu, copper is in my transition block right here. If I've got copper, I can't just give you copper on a problem. I'm going to have to give you copper with Roman numerals after it. And that is to tell you the kind of copper that you're dealing with. So I can't just say, here's nickel, here's silver, here's lead, here's copper. I have to tell you specifically the type of copper atom it is, because it could be various types when it comes to how it wants to bond and react. Again, having to do with electrons. So I lose my ability to be able to predict when it comes to transitions. So all of this block, these just kind of do their own things, and they're very important. All of these things are very important in their own ways and their own characteristics. I just can't put safe bets on them, whereas I can when I'm talking about group 1 and group 2. Alkali, yes, I'll tell you all about it. Alkali earth, tell you all about it. Transitions, I will tell you about it, but I have to know a lot of specific things to transfer. So with transitions, we'll just say capable of having very different atomic behavior. Depending on how those electrons are arranged and structured and how it's going to bond. So because they can switch up into many different conformations of themselves, we have to tell you so much information. Yeah, we'll give you plenty of problems with transition metals. We're not afraid to do it. We just have to give you extra data. Whereas if I'm doing sodium, I just give you sodium. But if I'm going to do copper, no problem. I just have to give you some more information about copper. So we have alkali earth. There's my alkali earth. Now we've got transitions. Now we're going to skip, as we'll see in a periodic table later, we have different, if you look up a bunch of them, you've got different names. We obviously know are metalloids, but you have different names for some of these groups. One of my favorites that I can't remember if I put it on here, it was, I think it was called the poor man's metals or poor man's transition metals. I can't remember. It was a sadly hysterical thing. I hadn't really ever seen before that saying or phrase for how people were labeling these families. So in my alkali, earth, and transition metal family groups, I'm now jumping into nonmetals, and notice I am specifically jumping over some groups into a much more reliable group 17, which is my halogens. Okay. The reason we kind of jump these is because you'll find that in some of these cases with these groups, while every atom in each group behaves similarly and reacts similarly as every other atom in the group, the only difference is size, how many protons, neutrons, and electrons each have. So the smallest are up here, largest down here. As we make that movement, what's going to end up happening is that you've got non-metals on top and you can transition to metals on the bottom, and it gets a little awkward in terms of being able to call them a singular family, because you'd expect them to all be, these are all very reactive metals, these are all very reactive, as we'll learn, non-metals. But what happens when you get situations where you start with non-metals and you finish with metals on the bottom? It gets a little weird. So we kind of skip over those because they have their own kind of rules going to. Two very predictable non-metals. So group 17 is, like I say, I'll call it group 17 a lot. Those are also called our halogens. And they are known for being the most reactive and desperate to bond nonmetals that exist. So if it does so happen that you see that a lot of times we have alkali earth or alkali metals hooking up with halogens, there's a reason. Most reactive metal, most reactive nonmetal, both families and groups are desperate to be able to bond, and they love to bond together. Man, do they love to bond together, as we will see. So that's all I'm going to put down for there. Halogens, most reactive nonmetals. But clearly, we use it so much, we want you to know names. Alkali, alkali earth are transitions. And then we'll jump over to group 17, or our halogens, for our most reactive nonmetals. Nonmetals, like I said, if you look it up online, you'll see different names like chalcogens or chalcogens, depending on how you want to say it. You know, we have some of these that are named very different, unique things. We're bundling them here in our nonmetals. So I'm not going to go into properties, but they do get predictable in terms of their bonding. So most predictable would be our halogens, but I can also do very good predictions based on behaviors of nitrogen, carbon, oxygen, etc. I can predict pretty well based on their electron structures. So I'm going to actually in the metal, non-metal, metalloid video, we'll get into those properties. But one thing I'll just really quickly jump into is when we write formulas and compounds, and that's something in the next month or so, usually around the holidays, we dive hard into being able to write a formula if I give you two elements that bond, or being able to name a formula if I give you the formula. So naming and writing compounds is a huge thing that we do. Well, how you do that depends on what's bonding. Notice, in my nonmetals, when nonmetals interact and bond together, they form a certain kind of very strong bond called a covalent sharing bond, and you name them differently. And they have the ability to make many, many combinations with just, say, carbon and oxygen. With just those two, they have the ability to be able to have different numbers of C's and O's in different CO compounds. That is very different from when a group 1 metal and a group 17 non-metal get together. They can only make one thing. There's only one compound that sodium and chlorine can make, and that is NaCl. That is all. There is no such thing as Na2Cl, NaCl2. No, that's all they got. And that is all that ever will be. So chemistry is locking those into place. Why? So that's something we will learn. So I just wanted to throw out nonmetals, sure. Properties, it's not that they aren't reactive, they are just reactive differently when they react with each other. Okay, and then finally, the snobs at the end, the snoots. So group 18, noble gases. This is one that strangely a lot of people know about. Noble gases are not reactive. They do not like to go find partners to react with, to share electrons with, to give or take electrons from in exchange. No, they are happy being non-reactive on their own. So key property here they will avoid reacting. It's not that it's impossible, but we'll learn again, it's all about electrons. So that's the big secret that we keep coming to, that we're going to get to. Because of how electrons are stored and their energy levels and outer energy shells, as we'll learn, these are happy. They don't need to be able to bond for anything. The bottom line is, when we get down to chemistry, the reason anything bonds with anything is because it is seeking some sort of stability. And it is seeking a different level of being full, being whole. And how we define that is all triggered around electron formation, how many electrons they have, where they keep them, and then it becomes a giant game of trying to be able to, that they don't know they're playing, of trying to be able to get the most stable, the most satisfying number of electrons in the right places. Noble gases already have all the electrons they need in the perfect places for them to be. They're just that way. Lucky them. So they aren't on the prowl to be able to react with anything in any way. Are noble gases. And again, noble gases. This is the prize that you win for many different things. So whoever won the Nobel Prize in chemistry, I don't think made the presentation. So, noble gases. Let's see. That takes us to the end. So these are the ones I want you to know. Are noble gases that don't like to react. Are non-metal groups that do like to react, but in a different way. And then we get into our halogens, our most reactive nonmetals. Okay, far and away, no doubt, and there's a reason. And then transitions, very reactive, except reactive in many flexible forms. So you can't just say, hey, here is silver atoms, go. Bond them up, tell me what happens. You have to know the type of silver atom you're dealing with and how it's going to behave. And then you can make predictions on how it's going to bond, what it's going to form. But all transition metals can take a variety of personalities when they come to bonding. So it's very hard to work with them academically. And then we get into our alkaline earth, group 2s, very reactive. And the most reactive, group 1's alkali metals. So, like I said, I will go back and forth between group 1, group 2, group 17. I tend to call these halogens more than I use alkali earths or alkali metals. So, that's a quick dive. We will get into lanthanides and actinides. Why did we pull these out? Why do they have to come away and be able to be on their own down here? There is a reason. It all has to do with numbers. So when we start looking at how we pack away our electrons, a little foreshadowing, when you see these little sections of the periodic table, you kind of look like buildings. There's a tall one, there's kind of a square, there's the middle block here, and then there's this whole separate area going on down here. The numbers involved in those areas are critical and important in telling us where electrons are, live, and then predicting how things will operate. So that's a quick journey into families and groups. So like I said, period, everything in the same row, yes, very, very fundamental, big things in common. But when you want to start getting detailed about reactions and predicting reactions, that comes from our groups. Okay? So that's hopefully just riveting, stimulating, and you're going to go cry with the emotional release of the inspiration that you just received. Again, purposely not telling you anything about one of the most important things the periodic table will tell us about. But we'll get there. So that's the difference between our rows or periods versus our columns and groups / families, and why we call them families, because they all have common behavior with each other. Super cool. So that's that for now.